student at MIT, and today I'm going to be talking about a slightly different type of AI from what we've been hearing about. I'll be talking about spatial AI.
Executive of Bangkok Bank and our dear colleagues. Welcome to the AI and Robotics Hackathon and Competition 2025 live in Bangkok. Fernandez, the President of Bangkok Bank. Please join me again, once again, give him a warm round of applause, please.
Professor Joseph Paradiso, Director of Responsive Environment Group, MIT Media Lab, Kuntipaporn, Cloud 11, Dr. Zhao, MIT ASEAN Office, ladies and gentlemen. On behalf of Bangkok Bank, it's my great pleasure to welcome all of you to this AI and Robotics Hackathon and Competition.
Hello everyone, thank you so much for having us today for this very important event at Bangkok in person. My name is Mirei. I'm serving as the Director of Member Relations at the Media Lab. So happy to be here. And I'd like to just give you a very quick overview of the Media Lab just in case you're not really aware what we are doing. So Media Lab is very well known for art, design, science, and technology. We just do a lot of research at the Media Lab, but we put a lot of effort into art and design. The Media Lab is well known for that interdisciplinary research lab. If I say traditional disciplines as a dot, we work in between. There are a lot of disciplines, such as, say, chemical engineering, mechanical engineering, biology, computer science, you name it. We work in between and look for a new discipline to explore, and that's what we are very good at. The Media Lab is putting a lot of effort into sharing policies, governance. We have just a wide range of research at the Media Lab. Very similar way, we have smart materials or IoT, and this time we have 5 research groups plus mechanical engineering of MIT. 10 of us are here to Bangkok, and we are willing to learn from you. And I hope this can be a very good learning opportunity for everyone. Thank you very much.
More things. We take a reference video of a user at the same time as we can collect their physiological signals, and we optimize the model to be custom to that individual person. You might have different relative strengths of your various muscles, and by customizing, we lead to the best possible functional outcomes that we can. And as a result, this leads to having really dexterous, intuitive, fluid control where we're trying to apply that dynamic predictive controller. And on top of that, this is enabled by the AMI surgery that allows them to have muscles that function dynamically together, reducing unwanted muscle activity and resulting in improved control and functional outcomes. Very few degrees of freedom in the hand, and do flexion, extension of the thumb, rotation, each of the 4 fingers. And this also connects to a wrist piece that I didn't bring with me, but would allow rotation of about the wrist. This hand weighs 490 grams, which is slightly less than an adult human hand. It's also about the same size as my hand. And it can go full open to full close in about 200 milliseconds. So it's really quite fast, really quite dexterous. And this is the only way I'm able to get a lot of these great functional outcomes with my users. So, pull open the laptop. Okay, that's a video, right? I'll pull open the laptop and we'll move on to the next piece a little bit here about how I actually collect the data and train these controllers. So, point to the rest of the hand to come up with this estimated position in 3D of a 2D video of the hand. So what I do with my prosthetic users is I ask them to, with sensors placed on the residual limb of their amputated side, mirror their movements with their intact hand with their other hand. And if they do the same movements at the same time, I have an input-output training data set for training this optimization for working with this neural network. So I have the input of the muscle activity that produces. I'm just going to throw this slider down so I can just keep moving my hands over here. I have an input training set that consists of the muscle activations while they do a number of different movements, and I have the desired output, which is the actual movement of the hand. And we have these timestamps as somebody does a number of different movements with their hands, and these are used to train the neural network, customizing it to the user to create a specific model, controller, neuromusculoskeletal model, biophysical model. These are all terms that I would use. And then we use that to run to predict control signals from the user, to predict their movement intentions, and send those as commands to the prosthetic hardware itself as we do a number of our control tasks. So, with my last couple minutes, I'm going to just sort of summarize pieces of this and talk about the current state of my research. So, the ultimate goal, of course, is to restore the full ability of somebody with to restore the full ability of somebody with a prosthetic hand to live independently, to complete all their activities of daily living, all the tasks that they're really interested in being able to do. And we do this by trying to emulate the function of the intact human body. We're using the fact that evolution has created all of these great structures and systems. We're taking advantage of the fact that from here, the brain, down to the level of the amputation, everything is intact, so I don't need to try and recreate some aspects of that wiring. I can pick up the signals peripherally within the limb itself, and then use those as control signals the same way that those signals are interpreted within the body in order to be able to predict dynamics, to predict the kinematics, and ultimately lead to fluid, dexterous, and intuitive control of prosthetic hands. So I think I'll leave it there, but thank you all, and I'm glad to be here.
Hello everyone. Annika. Super excited to be here and talk about our research on cognitive copilots. So, I come from the Fluid Interfaces group in the MIT Media Lab, where the thing that we work on is trying to figure out how can we use technologies like wearables, brain-computer interfaces, and artificial intelligence to essentially help us with cognitive skills. And over a month, and we found that people who were using ChatGPT were processing the information less in their brain, and they were also significantly worse at even remembering what they wrote about it. We also had people use an AI system over a month in order to get information and figure out what is the true and false information that they see. And we saw that if people always had an AI system, they were getting better and better at telling what was true and what was false. So this is using ChatGPT. And then it gives you, excuse me. So it gives you audio feedback every time someone says something that might be false. And then if you're curious, you can look at it and say, oh. So, we also have people in our groups who are working on wearables for
Hi, nice to meet you. I'm Robert. I'm an investment banker from Global Investments. And what do you do that? So we invest in various startups that help with rare diseases. But you should reach out if you're interested.
Thank you.
Robert.
So yeah, very, very useful. We also have a student or group 80% accuracy, have people tell where things were behind them without them being able to see and look. Okay. So I hope this gives you an idea of some of the cognitive agents or cognitive co-pilots that I'm working on in my research. We want to make sure that AI system that AI technologies is not something that makes us worse at doing things, but we want to make sure that the technologies we're building both help us.
So before getting into the research, I just wanted to give you a brief introduction about myself and my academic journey, and as I see that there's a lot of students here as well thinking about grad school, so I wanted to talk a little bit about that. So I was born and raised in South Korea, so I was there until high school, and there one thing was drawing my attention. So the question, what is the relationship between human minds and body? And starting from this question, I started to get more deep into physics, thinking about how our body is in relation with the world, and looking into philosophy and thinking that it would unlock some keys to the insights of how we process, how our mind processes the world and how we relate to the world as well. And that's better, but it's about how can we use the technology to make us flourish in the world. And there's a lot of different kind of programs if any of the students are interested. And we also have speaker series every week where you can online kind of look at different kind of insightful research in the human flourishing field. And these are some of the core research areas that we're really looking into today. And specifically today, I want to talk about my research in these 3 different areas where I really look into user agency, where we're designing AI system where human is at the center, and what is a sense of purpose? How can we support senses of meaning in the world with AI as we interact? Emotional well-being as well. I applicate smart glasses, smart watches. So applying this framework to my research, I specifically look into these questions where there's this world where intelligent system now can sense and interpret our body signals, emotions, and how we act.
Hi, yeah, so my name is Lucy. I am a PhD student in computer science at MIT. And so I am a part of the Multisensory Intelligence group in the Media Lab. The goal of our group is to create human-AI symbiosis leading to better collaborative decision-making between humans and AI systems. So that we outsource to be printed by a flexible circuit board company. And the technology here is based on the piezo resistance. So there is an intermediate piezo resistive layer that is sandwiched between these flexible circuit boards, so that when you manipulate objects, it applies pressure to different regions, and therefore we can sense what is actually happening, what your hand or your skin is feeling. All these components, all the other components are just very easily 3D printed in our laboratory, and the final assembly here takes about 15 minutes. And the total cost of a personalized glove for your hand is about $130. So what can we do with this data collection method? Well, we have an ongoing project in our lab to create a large-scale benchmark of both vision and touch data. So if you think about building the next generation of robots with humanoid and dexterous hands capable of fine-grained, flexible manipulation, we need to collect lots of data on how humans actually manipulate objects. So here's a video of someone wearing our glove. And on the right is this pressure sensing data that is being picked up by our glove. And also we combine this with camera data. So from the video of the human manipulating the environment, we're able to estimate the 3D position of the hand. I came to detect peanut allergies. So in the beginning, this sensor is nowhere near this jar of peanut butter, and so our model shows that peanuts are not detected. And as you can see, as the sensor approaches the jar of peanut butter, all of a sudden, our model detects there's a peanut allergy. And we also hook this up to a large language model, so you can get personalized real-time advice if there is a hazardous substance that you might be allergic to. Cool. So that got is using an LLM backbone, and the final model is a reasoning model. So when you ask it to help you with a diagnosis, it actually tells you its chain of thought as well as highlighting the input data to explain how it came up with this prediction. And to train this, we came up with a new reinforcement learning algorithm to handle the fact that when you have all of these different data sets, some are easier than others, some are more representative than others. And so what our algorithm does is that it does dynamic scaling. So during every single iteration of training, it does a clustering algorithm to determine which subsets of the data are easier or harder to learn, and it dynamically rescales how much the model weights performance on each of these data subsets. So one thing that I will highlight here is that we are able to beat many of these prior reinforcement learning algorithms. So PPO was the original algorithm used to train ChatGPT, and then GRPO was used to train DeepSeek R1 and also the country models. And our algorithm, DRPO, is able to outperform prior work by about 20%. Finally, here are some example outputs of how our model works. So it's a truly multitask model. So it can handle both problems such as predicting the duration of a patient's stay, as well as existing cancer diagnosis. And so for each of these problems, the model is able to explain its reasoning and also highlight for the clinician like why it came up with that based off of the multimodal data. So in our lab, we know that the future of AI is multimodal. And in fact, it's quite obvious because this is how humans understand the world. But the obvious thing is actually very difficult to do. So we're attacking this problem from all angles, both in low-level sensing and trying to incorporate and collect data on all these different modalities, and also coming up with new models and new paradigms for training these models. So I'd love to talk to all of you about if you're interested in multimodal learning and creating the next generation of foundation models. Thank you.
Thank you, Ms. Zhao.
While we sleep, we don't detect it because we're sleeping deep, but a wearable can detect it, and this can be used.
So Annika, thank you for having me here. I'm really excited to talk to you today about my research, which is around multimodal AI and engineering design, so exploration and evaluation at scale. So by way of introduction, my name is Kristen. My background is in mechanical engineering. I have my bachelor's and master's degrees in mechanical engineering, and I'm currently a fifth-year PhD candidate at MIT in the Decode Lab, where our lab focuses on AI in engineering design and manufacturing. So one of the aspects that makes AI within engineering unique and challenging is the state of data sets in engineering.
type of AI from what we've been hearing about. I'll be talking about spatial AI and how we can build 3D models using these types of different inputs we've talked about. Specifically, I'm going to be talking about world model. Thank you.
Last talk, it's both an honor and a challenge to go on after so many brilliant young people talking about their work here so well. So we're lucky to work with people like this at MIT in the Media Lab. And I'm also keeping you from eating your lunch, but even more than that, starting this amazing hackathon. So I'll do my best to be efficient. I'm going to go through a whole bunch of projects that are going on in my group and go through them very, very quickly, so you'll get kind of a taste of the work we're doing. So instead of going down deep like the other talks tended to do, I'll be moving very quick, but I'll try to keep you entertained. My group looks at putting sensors into interesting and relevant places at different scales, and then trying to connect with people in different ways to create new kinds of interactive experiences. So we do a lot of work with wearables. This is a slide that shows some examples. This is actually my student, David Ramsey, who built sensors to look at things that are a little bit different than the usual sensors, right? We became very, very well known in my group for doing wireless wearable sensing, for Internet of Things, and for measuring how people move, working a lot with sports players, people that have difficulty walking and things like this. Building wireless sensors to measure these things, and make different kinds of interaction. But then we moved into sensing things that were less perceptible. So things like your sense of comfort in a building. You know, are you hot, are you cold, can you gauge your comfort? Things like your focus and attention. And that's what David was doing here. He built a whole bunch of sensors to try to measure and track attention. And we're funding the attention battle online. We're going to be funding this as well in the real world. And David's making different kinds of devices to quantify this, to see how experiences translate into real world things and how our focus and attention can be conserved. And then we have a lot of sensors for smart buildings, looking at how buildings work, sensors in environments. We've done a lot of environmental sensing deployments in my group at large scale, different places. But we also work with virtual worlds to try to bring this information up close to people, taking the sensor information and bringing it up as kind of an animation or a soundscape. The term cross-reality actually came out of my group from this work. And we're living in an era now where, you heard in the last talk, space is very accessible now. We start thinking about putting things into space we've never even considered before. And that little robot, this hackathon is all about robotics. This little robot here was built on my student Feng Zhang. It is now sitting on the surface of the moon. So we launched that to crawl on top of one of the bigger rovers. It landed on IM-2, a portion IM-2 didn't land straight up, it fell over. Hopefully they get it right the third time. One of the interesting frontiers for sensing and wearables, kind of where they come together, is in e-textiles. You heard a little bit of that in some of the other talks. E-textiles actually have a long legacy in the Media Lab. One of the first groups to start looking at that, working with silk organza coming from India. That's a fiber where they wrap conductors around the fiber. You get conductor thread. Very early way to do that. But we keep innovating in that space. This is work by my student, or now alum, Mirei. He is now professor at NUS in Singapore. But he did some amazing work in the group, having these sensing structures that just come off of a knitting machine. So you put in different kinds of weaves that can sense things, you use different kinds of conductor threads, so you can sense pressure, stretch, proximity, lots of other things in the e-textile. He did many things. He did things at the architectural scale to measure interaction with people, smart carpets, measure where you walk, how you move, working with dancers. Smart shoes to look at profiles, with how you walk, great fine-grained sensing in these things. Is from the Media Association report. It's measuring position with capacitive sensing now. So your non-contact height and position along the keyboard. And now when you touch, you know that. From capacitive sensing, you measure pressure and piezo resistance as well. I know of no keyboard that you can stretch. up yet many talented musicians. This is a student Mike, just putting it in properly. So again, textile in a totally different aspect. That's old style sensing, where you basically have a wire more or less going to every sensor happening in a matrix, where you basically have to have lots of connections coming into one big hub. It doesn't scale very well to large surfaces. Our body, look, we have a lot of neural fibers that go to the brain, but they synapse and they process as they go. The signals. So it's our sensor tape now becoming really a component of any textile thread, sensei thread. And we're just amazed at the different things you can do with it. Set it into your taste. We have so many more ideas of where we can put this kind of a technology. I'm using flex PCBs and flexible interconnects, stretchable interconnects. He can put it down on the fabric, and he's done it in a wearable himself. He's got a whole kit of these serpentine connections that can stretch. Toronto Beijing, who took a whole bunch of vibro-tactile actuators, put them in a smart network, and would control them so you could begin to feel different kinds of complex haptic phenomena all over your body. In this case, he collaborated with Fernandez group at APFL, one of the leading groups in the world on drones, to think about drone swarms. How do you represent the drone swarm to people? How do you connect people to a drone swarm so you can begin to feel it, relate with it closely? Not just look at some abstract visual. Try to compensate for things like hearing losses. People like me get older, we go to really loud concerts. Can you start to augment the lack of perception? When I'm in a crowd, I take what people say, and Thai people have very wonderful that. We had a project. He said, no, I also want to do magnetic stimulation of peripheral nerves. It turns out if you put a large magnetic pulse into your arm or leg, you can actually activate the nerves and feel a twitch or make your muscles twitch. Without having to wire it, or have a haptic actuator that shakes. So Mirei was fascinated with doing this on the arm, and he made this coil. This is a thing about smell. We put them in the area where people breathe. So we made a set of glasses that has many sensors. Some sensors look at your mental state, look at cognitive load, look how just distracted or attentive you are. Look at eye blink, things like that, with different modalities, but they also look outward, measuring air quality here, right above the bridge of the nose. We put different kinds of sensors here. We use Botswana, or goes to Chile, and start to do that. And